close, PowerPoint, start. Okay, so we're going to continue with statistical distributions, and we're actually going to come to one of the most important distributions in A-level maths. We're going to be looking today at the binomial distribution. Before we look at the formal aspect of the binomial, let's actually try and figure out why it might be useful and where our usual techniques are no longer efficient to use. So, we've been looking at probabilities, and we've become very well accustomed to tree diagrams and how we can use tree diagrams to calculate probabilities of specific events. If I asked you, looking at this tree diagram, to tell me the probability of achieving one green, so we spin the spinner, we're going to spin it twice. What's the probability that I get one green when I spin that spinner? Well, it's either going to be red followed by green, or it's going to be green followed by red. So we can quite easily and quickly calculate the probability of achieving just one green. There were only 2 trials here. What if I was to expand that? And I'd say that actually, what if we have 3 trials? Okay, it takes a little bit more work. We need some more space to produce this tree diagram itself, but we can go ahead and we can find the probability of one green. How many different ways are there to achieve one green? We can go ahead and do that calculation. I think 3 trials is probably as far as you should be going with a tree diagram. Anything beyond 3 trials becomes quite cumbersome. It becomes difficult to work with. The tree diagram itself is unwieldy, and it's a little bit hard to track down all of the possible outcomes and to make sure you've picked up all of the permutations or should I say combinations that satisfy your criteria. So once again, would you be able to tell me all of the ways in which we can achieve one green if we've spanned this spinner 4 times? So 4 spins on the spinner. Here's all the different possible outcomes. How many of them have one green? Now this is quite labor intensive, and it's going to take time. It's going to take quite a bit of time to find all of the outcomes which satisfy our criteria. This is with 4 trials. What if we had 10, 20, or even 50 trials? There is no way a tree diagram is going to be an efficient way for us to calculate any of those probabilities. So here's where we actually have to employ a model within statistics that can help us to do that work instead. And the model we're going to be looking at is the model of the binomial distribution. So we'll go through some criteria and when best to use it. So what are the situations that lend themselves to using the binomial distribution? So you can model a random variable with a binomial distribution, and here's the notation. We write B for binomial, we open up some brackets, and we're going to put 2 parameters. N is going to be the number of trials, the number of attempts, the number of times you span the spinner, while P is going to be the probability of success. Let me go through all of the criteria for you. So there needs to be a fixed number of trials. We need to know that this experiment is going to be repeated a specific number of times. There are some questions we come across where I might say I'm throwing darts at a dartboard and I'm going to keep on throwing it until I score a bullseye or until I hit the bullseye. That is not a fixed number of trials. We don't know at the beginning how many darts I'm going to throw. We just know the condition where I stop throwing darts. We specifically need to know the fixed number of trials. There will be 8 darts thrown. Whether I hit the bullseye or not, I'm going to throw 8 darts, no fewer, no more. When I've thrown 8, then I stop. It needs to be a fixed number of trials. The context should be able to lead you to whether or not that's the case. So in the tree diagram I'm working with before, N, there is a fixed number of N. We span that spinner 4 times. There were only 4 spins. We didn't stop after 2. We didn't get a bonus spin. N was fixed, 4 spins. The second criteria that we need, and these criteria are important, so make sure you memorize these. You need to write these down. They're often referred to in exam questions, and you need to be specific in context of these criteria. The second criteria is that we have to think about our situation as having 2 possible outcomes: success and failure. There should be no middle ground. There should be no third option. There needs to be just 2 possible outcomes. And that's where the name binomial comes from. We know that the prefix bi means two. Bicycle, binoculars. There's so many words where the prefix bi means to have two. Here we're talking about success and failure. Those are the only two possible outcomes, and we need to reframe our scenario in terms of those. If we were thinking about a football match, usually we think there's three outcomes to a football match. You can win, you can lose, you can draw. If we want to model the result of a football match as a binomial, we need to think about win and not winning. We need to think of the complement, win, not win. Or we can think about lose and not lose. We could even think about draw and not draw. We have to combine outcomes into two distinct events. One of them would refer to as a success and one of them as a failure. In this scenario, success was getting green on the spinner. We were looking for one success. We only wanted one green. Any other color that we achieved, we would look at as a failure. So there should only be two outcomes, success and failure. And there is a fixed probability of success. So we don't want a tree diagram scenario where we're taking something and we're not replacing it, because we know that that changes the probabilities for each subsequent trial. We need those probabilities to be consistent all the way through. This would always be with replacement. This would always be independent events where one of them, or the first trial, does not affect the second. The second trial does not affect the third. We need the probability of success to remain constant, to be fixed. And an additional fourth one is that we need these events to be independent. But that usually goes hand in hand with the fact that we have a fixed level of probability. We have that constant probability of success all the way through. But an exam question may well ask you, why does this situation fit a binomial distribution? And we would need to refer to two or more of these criteria. Okay, if a situation fits these criteria and we're happy that we can use the binomial distribution to model it, we can make use of the binomial probability function. This is the binomial probability function. The probability that x equals r equals NCR, this NCR statement we'll look at in a second, probability of success to the power of r, and the probability of failure to the power of n minus r. If you do this calculation, you will find the probability of r number of successes. This statement is true if our situation fits the preceding criteria. Okay, let's have a look at exactly how we could have used this in our previous example. Here's the distribution. X follows a binomial distribution of 4 and 0.4. There were 4 trials. The probability of success was 0.4. Remember, success was achieving green on the spinner. Okay, so here's our distribution, and this is usually worth a mark in an assessment, being able to interpret the context and write it in this mathematical model format. Let's go ahead and substitute into the probability function. The probability that x equals 1. We looked at how to read this before. The probability that the total number of greens that I achieve when I spin a spinner 4 times will be 1 equals this statement. It's 4 NCR 1. 0.4, the probability of success, to the power of 1. 0.6 to the power of 3. Some things I want you to spot straight away in here. The R value is at the bottom of the NCR statement, and it's also the power that matches the number of successes. The probability of success and the probability of failure will add together to equal 1. I like to call the probability of failure Q. Some people call it 1 minus P. But I'd just like you to learn that Q is 1 minus P. They're the complement of each other. Those numbers should add together to give you 1. They're the only 2 possible outcomes. And the powers themselves should add together to give you the total number of trials. So that should be your sense check that you've even written this statement correctly in the first place. This goes into your calculator. I'll show you exactly how to put an NCR statement into your calculator, and we get an answer of 0.3456. What does this actually mean? Why does it work? Firstly, let's have a look at the probability that we would calculate if we took each of these routes. Here's one route that gets us 1 green. If you notice, we have 0.6 multiplied by 0.6 and another 0.6 and a 0.4. Because these events are independent, if I took a different route, I would still be multiplying those same numbers, those same probabilities. I have 3 instances of 0.6 and I have 1 instance of 0.4. Here's another way around that we can get 1 green. I have 3 instances of 0.6 and 1 instance of 0.4. And here's the fourth way round. I have 3 instances of 0.6 and 1 instance of 0.4. All of the routes that I took were going to have exactly the same calculation. They were going to have 0.4 to the power of 1 times 0.6 to the power of 3. Well, if I just multiply that by the number of routes, the number of journeys that I can take that achieve 1 success, I would find my answer. The NCR statement calculates for us how many different journeys we can have that have 1 success. How many different combinations of 3 reds and 1 green we can have. How many different combinations of 3 failures and 1 success we can have. And with this example I've got in front of us, you can see we either have success on the 4th attempt, or on the 3rd attempt, or on the 2nd attempt, or on the 1st attempt. There's 4 different placements for that success amongst the 4 trials. So, the probability function really is calculating how many duplications of our product of probabilities. How many times do we need the calculation 0.6 to the power of 3, 0.4 to the power of 1? Well, the NCR statement is going to do that for us, and we just need to locate it on our calculators. You're going to want to hit the options button, and then we need to scroll to the right, so F6 will do that for you, and we're looking for this probability menu. F3 for probability, and there you see we have a factorial button, a permutation button, a combination button, and a random number button. We're looking for the combination button, the NCR F3. So you're going to press that to get the C appear on your screen, and 4C1 will do for now. I've tried on purpose to have a low value of n so you can actually see what's happening. But once again, extrapolate this. Imagine this if there were 50 trials. We definitely can't do that by hand. And there's no way that I'm going to be able to show you all of those combinations on the screen. But we know that our formula is scalable and it works at that larger scale as well. Okay, let's have a look at another example. So we're still working with the same distribution. So n equals 4, p equals 0.4. The probability of 3 successes we want to find now. Our NCR statement is going to tell us how many combinations there are where we get 3 successes and 1 failure. We know that we're going to have 3 instances of the success probability and 1 instance of the failure probability. We're going to have 0.4 to the power of 3, 0.6 to the power of 1. Well, for NCR 3, you can check for yourself on your calculators. There are 4 different ways this can happen. The same way there were 4 placements for 1 success amongst 3 failures, well, there's also 4 placements for 1 failure amongst 3 successes. The failure, or achieving red, can happen on the first trial, or it might happen on the second trial. It might happen on the 3rd trial, and the only other place it might happen is on the 4th trial. There are 4 different placements for that 1 failure. There is some symmetry to the NCR statements, and this all links to Pascal's triangle, and we will look further into some of its features in a separate video. But here we just need to really appreciate that it's telling us how many different routes we can take that have that combination of successes and failures. Okay, in our calculator, we can easily get our answer. What about if I wanted 4 successes? How many ways can I get 4 greens if I had 4 attempts? And you could type into your calculator 4C4. What would you get? 4C4. There is only one way that this happens. The only way is that I get green on the first attempt, green on the second attempt, the third and the fourth, all attempts come out as green. There is no other route through this tree diagram that will get me 4 successes. 4C4 is 1. There is only one route to take. Looking at the probabilities, I have 4 instances of the successful probability. I have 4 instances of P. I have 0 instances of Q. I have 0 instances of a failure. 0.4 to the power of 4, 0.6 to the power of 0. Now, if you're on the ball and you're thinking about this, you'll realize if 4C4 is 1 and 0.6 to the power of 0 or anything to the power of 0 is 1, the only meaningful part of this calculation is the 0.4 to the power of 4. This is what we call an edge case. Because there was only one way that it could possibly have happened, it's actually quite a quick and easy calculation. It's probability of success to the power of 4. All of them were successes. Similarly, if there were 0 successes, there's only one way that can happen. Failure, 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 failure. Red, 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 red. And in that case, it will be 0.6 to the power of 4. Once again, we will explore the NCR values and even this probability statement further in additional videos. But for now, we want to make sure that you can use this probability function for any scenario that you're given. Okay, and just to cap it all together, this is the notation for the distribution. This is what the distribution would look like if we were to graph it. This is a discrete distribution, so there are no outcomes in between 0 and 1. We want to try our best not to indicate graphically anything happening in between 0 and 1, nor between 1 and 2, 2 and 3, etc. But this is the probability of 0 successes, 1 success, 2 successes, 3 successes, and 4 successes in a graphical representation. And here we have it as a discrete random variable probability distribution. The sample space written out, all of the possible outcomes to the event of the number of greens that I achieve when I spin the spinner 4 times. It can be anywhere between 0 and 4. And we've matched each of those with the appropriate probability. So this was the binomial distribution. 2 possible outcomes, constant value for the probability of success. Each of the outcomes must be independent. And we have to have that fixed number of trials. So 3 representations and the probability function that we've looked at. Okay, let's go through some examples. So in this case, x follows a binomial distribution where n equals 12, p equals 1 over 6. We need to find the probability that x equals 2. Let's go ahead and substitute into our probability function. N is 12. R is 2. P is 1/6, and we want 2 successes, so that's 1/6 to the power of 2. Failure is 1 minus a 6th, or the complement of 1/6. That's 5 over 6. If we have 2 successes, that means there were 10 failures, so it's 5 over 6 to the power of 10. We calculate that, and we get 0.2961. Similarly, the probability that x equals 9. N equals 12, R equals 9, probability of success to the power of 9, probability of failure to the power of 3, and that gives us quite a small answer here, 0.0000126. And finally, we're looking at a cumulative probability here. The probability that x is less than or equal to 1. Well, let's start by thinking which outcomes we're interested in. We're interested in the probability that x equals 0. And we're interested in the probability that x equals 1. Nothing else satisfies this inequality. So we're just going to use the probability function twice. If you remember, 0 is an edge case. So I don't even need the NCR. I don't need the probability of success. I'm just going to have 12 failures. Probability that x equals 1. Well, n equals 12. R equals 1. success to the power of 1, failure to the power of 11, add those together, 0.381. Okay, so just want you to get fluid at being able to use your calculator to process and calculate these binomial probabilities using the binomial probability function. Okay, let's have a quick look at one in context. So here we're told that the probability that a randomly chosen member of a reading group being left-handed is 0.15. A random sample of 20 members of this reading group is taken. Suggest a suitable model for the random variable x, the number of left-handed people in that sample, and we have to justify our choice. So this is where we need to bring in the criteria. From the scenario we've read so far, what criteria would fit the binomial distribution? Well, there are two possible outcomes. There's left-handed, and we'll think about the complement of not left-handed. I also know that there are a fixed number of trials. There are 20 members, 20 individual repetitions of the experiment. And there's a fixed probability of being left-handed. There's a fixed probability of success. So that's my justification of why I would use the binomial distribution as my model. Okay, the second part asks us to use our model to calculate these probabilities. Probability of being exactly 7. I'm just going to plug this into the probability function. 20C7, 0.15 to the power of 7, 0.85 to the power of 13. And that leaves us with 0.016. The probability that fewer than 2 members in the sample are left-handed. Fewer than 2 is the same as saying less than 2. Now I want an equivalent statement that uses the numbers I'm interested in. So I'll go ahead and rewrite this as x being less than or equal to 1. 2 outcomes make up the event less than or equal to 1. That's the probability that x equals 0 and the probability that x equals 1. So probability function for each of these, add them together and we get 0.1760. So today we've looked at the binomial distribution. We've looked at where our usual techniques, our tree diagram technique, will start to fall short, and that's when we have a large number of trials. We've looked at the criteria needed for the binomial distribution to be an appropriate model for our scenario. And we've looked at the probability function and how we can use that to respond to specific probability questions. So get yourself some practice and come back as we move on to cumulative probabilities.